some more network to cover. And networks, we simply, if you're studying subsea systems, for many systems you're going to have networks. Okay, so you cannot escape to know. At least you should understand how to deal with networks. Okay, and then we will see the last part we need to calculate production profile is the effect of boosting. Okay, boosting is an option that I add energy to the fluid just to try to match that gap, right? You remember I'm to the right, so I have less energy, and then I want to add energy to the fluid. But to start that, I suggest, I prefer we start with pumping. Okay, we start with liquid pumping, and then after that we progress to subsea compression. Okay, so let's see if we go that far today. Okay, networks. We finished the topic of network. You get one homework. And then boosting, we also try to finish at least the liquid pumping part, but maybe part of it will be for next week. And that will be exercise set 3. Okay, actually an exercise on network and pumping. Okay, liquid pumping. We can delete this maybe in well. That's ESP. We're going to go back to that later. First, I want to say also there was a small mistake in the class from yesterday. When we are making this plot, okay, we should use the rate that is not going to change. Okay, in this case, the field rate, that's the one that doesn't change. Okay, here. So we shouldn't use here the Q of the well, because depending how many wells I have, that rate will change. Okay, so here I should have the Q of the field, that's not going to change, but then the curve will change depending on how many wells I have. Okay, so just be aware of that. Here I think we had yesterday Q well, it should be Q field, the rate that I'm producing from both wells. Okay, that's kind of an attempt to make a graphical explanation, but if you look at the equations, you see very clearly the reason. Okay, simply this WH, if this rate is higher, it becomes smaller. Okay. With reservoir pressure declines, then I will reach the required, will be close to the available. Okay, so yesterday we were first clarify how do we solve networks with no choke, and then the other thing we used was the graphical solution. Okay, we had a system that was like that, a very simple network. Okay, and then we decide to divide and conquer. Okay, we said this system, if we look at each one of these paths separately, and then we use the assumption that the pressure at the junction should be the same, no matter where you look it from. Okay, if you look from the separator, if you look from well 1, or if you look from well 2. Okay. Now, I want to add one more complexity, that is, what happens now if we have a choke in the system? Now, let's say again, that's the wellhead pressure, the wellhead. And then I have here the P junction, which is extremely, extremely close. And here I have the same. I have a choke, and I have here well 1 and well 2. And this will be PWH1, PWH2. Okay, but now I have a choke. So if you remember, what have we done when for the single well system, when we had a choke, what did we have to do? Okay, if we count the system of equations, right? Let's see equations, and then we have unknowns and equations. Okay, we have IPR1, we have IPR2, we have TPR1, TPR2, then we have the flow line. The flow line, we can call it flow line PR, flow line performance relationship. Okay, inflow performance relationship, tubing performance relationship, and flow line performance relationship. Okay, and after that we have the equation for both chokes. Okay, the equation of the choke gives you the delta P across the choke has a function of, what was it, the rate, right? And about the opening that I have on the choke. Okay, so how do we call the opening? Let's call it okay, let's call it CO, choke opening. Okay, and I have one equation for each. Okay, where CO1 is CO stands for choke opening. Okay. And if you make that, if you sum the number of equations, the number of unknowns you have, you're going to see it still is consistent. Okay, we have one more equation, but then we have the delta P. Okay, so we are able to solve that system of equations. Okay, remember, this equation is very ugly. Okay, it's an equation that has square root, that has a lot of things, requires sometimes iteration. So what have we done last time to avoid using the equation? You remember? We actually took it away, right, from the system. We said, this choke, we know we can deal with it this way. It's an ugly equation. We can solve our system of equation, but we can deal another way. We can simply take it out of the equation, right? And then we can calculate the pressure upstream the choke, P wellhead 2, right? P wellhead 1. Just before the choke, and we are removing the choke from the equation, and P junction here. Okay, we are not looking at the choke. So what have we done? What do we do, right? We come to the equation for well 1. Okay, we have wellhead pressure 1 versus Q1. It looks like that, right? And that's the sum of the IPR of well 1 and is the sum of TPR of well 1. Okay, these are these two equations. I go from the reservoir to the bottom hole of well 1 and from the bottom hole up. Okay, and I impose the rate I want, this Q1. That's the rate I desire. And then I get some PWF. Let me just remove this. PWH star. If I decide to produce that rate, right, I will have this pressure at the well. Then I do the same for well 2. For well 2, PWH2, remember the curve will be different in value, but we have similar shape. This is IPR2 plus the TPR2, the tubing equation and the IPR equation. Then I say I want to produce this rate, Q2 star. I go again to the curve, knock it, and read here the value of PWH2 star. If I produce this rate from that well, this will be well 2, then I will have that pressure upstream the choke. Okay. And the final step is to go to the pipeline that the pipeline tells you P junction has a function of Q of the pipeline, and it should look something like that, which here is only the FPR, just the flow line equation. And then you come with your flow line rate, Q1 star that you desire, plus Q2 star that you desire. And then you go and read then the P junction that I need. Okay? This is the one, these are the ones that I have. Okay, I come from the formation, I come up, and that's what I have. And this is what I need to flow that. Okay? So how do I know if those rates are feasible or not? If I can produce those rates? Q1 star is feasible. That means you're able to produce that rate only if PWH1 is greater than P junction star, right? You have to have a pressure drop across the choke, cannot be a pressure increase. Okay? And then Q2 star is feasible. Okay, I'm able to produce only if PWF-H2 is also greater than PJ star. And then I'm fine, I'm a happy man, I don't care. I can go talk to Schlumberger, Halliburton, find me a choke, but I know I can have this rate. Okay? Okay, so I can take out that complexity exactly in the same way. Here I don't have to solve the system of equations. Here it's very heavy. Okay, I have a lot of equations I have to solve. Here I just compute from the bounds and then I verify the condition. If not, well, I have to reduce the rate. Okay? That's what I tell. If reservoir engineer tells me I want this system to produce these two rates, okay, one of them is negative, I say, sorry, you have to reduce the rate. Now, in commercial software, okay, we use the first approach. So let's put a very clear distinction. So that's the second approach, which will be like a approach, okay, which is smarter. Let's call it that way, because you don't need iteration. Okay, no need for iteration. Okay, and this is the first approach, this one here, solving the system of equation. First approach. It's more general because you can also take into account those cases where the rates I cannot produce. Okay? Because how... So for the first case, let's say the reservoir engineer gives you Q1 star and Q2 star, right? So how do you solve, using this approach with the equation, how do you solve that problem? You have to use this two-layer scheme, right? You have to assume the opening of the choke, run your model, see if they are the same. No, run again another time, see if they are the same until you converge. Okay? You remember that was a long time ago, that discussion, okay? But that's the way you have to do. This requires, to get Q1 and Q2, you need two-layer iterative process. Okay, you need one to solve the network with a given opening. So let's say assume CO1 and assume CO2, then solve the network, and then you want to calculate Q1 and Q2, okay, and then you verify is the same as Q1 star and Q2 star, then solution. If not, then you have to assume back. So you have two layers. You have a solver and you have the other layer. Non-general, but more time this will be computationally expensive. Okay, let me see if I can move this a bit down or up, because I think okay. So now for the first approach, okay, let's see, for the first approach, it is sometimes useful to visualize the network has a function. Okay, has a mathematical function. I think it helps, at least to me, it helps very much to visualize it as a function. Okay, first you give as an input of that function. Okay, it's a vector function that depends on some vector input. Okay, that's my network. And here I need one input, which is system characteristics. Okay, these are system characteristics. And these are things like, for example, the C and the N of the wells. Okay, you need the CT, you need the S of the tubing, you need the S of the flow line, you need all of these data, and on top of that you need reservoir pressure. Okay. Then you have another input, which are not characteristics, but these are variables, decision variables, something that I decide. Okay, or I call it controllable variables. Okay, and in this case it will be the opening. Okay, what I choke opening I. Okay, choke opening of well I. Okay, you have a vector of these choke openings. And at the end, that function, after I solve it, okay, I give the characteristics, I give the opening. After I solve it, I'm going to get the Q of the well I. Okay, well rate. And then you're also going to get PWF I, you're going to get P wellhead I, you're going to get a lot of information. Okay. But these are controllable, or also called adjustable parameters. So the thing is that depending on the value of these controllable parameters, okay, that's going to affect this result. Okay, if I change these guys, it's going to affect my result. Okay, CO1, the choke opening has an effect on the results. So the way to visualize that, I'm going to make a plot for our system with two wells. Okay, for our two well system. Okay, we are going to make a very strange plot. Okay, we are going to put Q1, the rate of well 1 and the rate of well 2. Okay, and I'm going to plot the combination of values that I obtain running this function. Okay, so let's make one first. You say the first point will be when choke opening 1 is 0. Sorry, it's 100%. Okay, choke opening 100% open, and choke 2 is also 100% open. Right? I run the case, I substitute, the two chokes are open, run the network. Okay, solve the network. I'm going to get a pair of points, Q1, 1, okay, and Q2, 1. And I locate both rates in this plot. Okay, locate here. Let me make it just more space. this will be Q01, sorry, Q1 1 and Q2 1. So that's the combination of rates. When I have fully open choke, that's the combination I should get. Now, number 2 that I'm going to make, what happens if now I start to close one of them, leaving one of them open? One of the chokes leaves open and the other I start to close. For example, CO1, it's 80%, but this CO2, it's 100%. And I obtain Q2 2 and Q1 2. Okay, where is that point gonna be in that chart? First, which rate should be reduced? The rate of well 1 or well 2? Well 1, right? So, and it should be reduced from this open condition, right? But now, what should happen with the rate of well 2? Remember, both of them, it could be the same, right? But both of them are fighting for space in this pipe. Okay? So, when you reduce the rate of one well, then you have more space for the other well to flow. It's easier for the other well to flow. So if you're going to plot that, Q1 should be reduced. Okay? Q1 should go to that direction. And Q2 should go to that direction. Should be increased. Okay? So the point might be someplace here. Okay? Point 2. And I'm going just to put 2 just to avoid too many indicators. Okay? If I continue with that process now, close the choke one more, I'm going to get a line all the way up to here. A line or slightly a curve. It depends on the type of system I have. Okay, for dry gas, it's a fairly straight line. Okay, until I find this point where I have no flow from well 1, the choke is fully closed, okay, and only well 2 is flowing through the system. Okay, so here, let me make more space again. Okay, at this point, choke 1 fully closed, and maximum, this is the maximum of the rate Q2. Okay? And you draw that line. If you go choking, let's put here, choking well 1. I'm choking well 1. Okay? Now let's go back to point 1. Okay, let's make now a number 3. What happens if now I keep the choke of open, of well 1, 100%, right? But I take the choke of number 2, I take it to 80%. What should happen? Okay, should happen that Q1 should increase, right? Because now 2 is not competing with it in the flow line, okay? But Q2 should decrease, okay? That means Q1 should go in this direction, Q2 should go in that direction, and maybe the point ends up here, number 3. Okay, and then if you continue that process, you're going to get something similar, something like that, okay, where I have a point, here is choking well 2, and at this point it's fully closed well 2, okay, and maximum Q1. Okay, now comes the bit difficult part. Okay, so I have these 3 points. Okay, I run simulation with fully open chokes. I have one simulation with one choke open, one closed, and one simulation with one closed, one open. Okay, now I ask you, if I want a combination of rates here in the center, is it possible to produce that combination or not? If I want, reservoir engineer comes and says, I want to produce this Q1 star and this Q2 star. Is it possible? And let's say you have the area somehow. It is, right? Because if you choke both now, you should be able to find any rate inside this region. Okay? You should find any combination on that region. So this region is what I call the feasible rate area. Okay? And everything that is outside means that I cannot, the system cannot produce more. Okay? Even if it's fully open choke, cannot produce more. So this area is the non-feasible area. Any combination of rate, reservoir engineer tells me I want that combination, you say sorry, we cannot do it. Okay, we have to be inside the plot. Okay, so it's a very strange plot how to make it, but I think it helps you to find these two areas, okay, that you can have in a network. Okay, if you change the choke, you can have almost infinite combination of rates. Okay, you cannot have all of them, but you can have very close to a lot of combination of rates. Okay, by choking, making combination of choking one or the other. Okay, so it's a function that can give you infinite number of solutions, but you have to be sure the combination you want is inside that region. If you're outside, you're in trouble. Now let's take it one more step, okay, before we go to downhole networks. And the thing is that what happens with time? With time, when reservoir pressure is reduced, okay, is going down. What happens with that area, you think, when? And that's something very interesting. Okay, so remember we have an area like that, and that we have made for PR1. Okay, let's say assuming both of them are draining from the same. Let's not call it 1, okay? Let's call it original. Initial, okay? Let's maybe use the I. Initial. Okay. How do you think the area will change if reservoir pressure drops? It will shrink, okay? Why? Because if you say, well, if now my reservoir pressure is less, now the open choke point might be here, okay? I will be able to produce less from 1 and 2. Okay, so this is for reservoir pressure, let's call it 1. This will be for reservoir pressure 2, and so forth. Okay, so where reservoir pressure I is greater than reservoir pressure 1, which is greater than reservoir pressure 2. So if your combination of points, let's say they are here, they are going to be perfectly fine for all of these reservoir pressures, okay? But there will come a point where it becomes unfeasible. The area will shrink so much that they will become unfeasible. So in that case, you are going to ask the reservoir engineer, well, you have to bring it inside the map. Okay, you can have the rate in 2, but you cannot have the rate in 1, so you have to shrink and take it inside. And then after that, you will have to, if you go to the next pressure, then you have to again meet the line. You have to find exactly this point. Okay. So keep that in mind. I think the 2D example is nice. We can do it graphically. You go to more dimensions, you have to be Einstein, okay, to understand. But with 2D, you know more or less what happens, and then you can extrapolate to higher dimension. Okay. That more or less clear? Yep. Okay. So let's see now a way. I just want to give you because you're going to get an exercise. So how to solve this in Excel? Okay, you will be using Excel to solve this problem. So let's take that we have a system. Okay, example of solution. then I say I have the same case. I have two wells. Okay, I have a flow line, and I have, and let's say initially no chokes. So in my Excel sheet, I'm going to have, I think the best way to structure it is to have well 1, well 2, and then here to have flow line. Okay, you have in a table. And here you have reservoir pressure, you have C, you have the N, and then you have the rate, right? So you have Q1, Q2, but this one will be simply Q1 plus Q2. Now, one reason I don't like to, so you know what is the principle, right? You have to assume a rate or assume a pressure, and then you have to iterate to find the real pressure. Now, there is one problem to iterate with rate. Okay, with rate, if we iterate, so rate we use, the first thing we have to calculate is PWF, right? We have to move PWF, P wellhead, P junction. But if I iterate, if iterating with Q, the following could happen. Okay, that means I have this equation, right? C PR squared minus PWF squared to the power of n, and I want to clear PWF, and that gives me PWF is the square root of PR minus Q over C 1 to the n. Yes? The main problem with that is I don't have any idea how the rate should be. Okay, I don't know if that well should produce 1,000 standard cubic meter per day, if that well produces 10, if that produces 50, if that produces 1 million. We have no idea. So if we make a bad assumption for the rate, okay, then this number is going to be negative. And then I'm going to have it's going to be undefined. Okay, it's going to have an error. The solving process is going to finish. So because for that reason, okay, what I suggest is to change the order for this problem. On the other hand, PWF, you know what are the ranges that it could be, right? You know it has to be lower than reservoir pressure, and you know it has to be at least higher than separator pressure, for example. Okay, so you know a bound for PWF. Okay, so let's put here PWF, on the other hand, I know the bounds. Okay, I can specify the bounds. I know that PWF, at least in this case, has to be between reservoir pressure and has to be between separator pressure. Okay, so that's why I decide, or I suggest, you assume that number. So let's put here red, that's the value I assume. Okay, that's an input. From there you calculate the rate. Okay, you calculate Q, Q1 and Q2. Let's put it in blue, that will be the calculator. Okay, and then this one simply is the sum of Q1 plus Q2. And then you make sure you don't have this bad error. After that, how do I move? I move up to the wellhead. Okay, so then I need, for the wellhead, I need, let me just make more space to the left. Okay, for the wellhead, I need the CT and S first. CT and S. and then I have the bottom hole pressure, I have the C and the S, and then I can calculate PWH. Okay, so I can, this will be an input. Let's make it here. This is input, this is input, and this is input, this is input, and this will be output. Okay. Now you need, and what I can say is that now you have managed to come from the well, okay, up to here, and for the well up to here, but now you have to have this part, okay, this pipe. So for that, I suggest it will be maybe different on the exercise you're going to get, but see flow line, and here the P of the separator, and you're going to have simply one value here, C of the flow line, P of the separator, and with those two you calculate the pressure at the junction. Okay, let's call it junction instead of wellhead pressure, junction. Okay. So you can use actually these two guys to compute. Okay, one of them you go co-current, you go with the flow from reservoir, bottom hole, and junction, and then the other one you come, actually you have this rate, and then you go backwards to find that number. Okay, if you're going to have a solution, what should happen here? If these PWF that you assume are correct, let's make it maybe like that, so it will be our decision variable, okay, with a different color. Then I have to make that all of them are the same. Now that's a bit tricky in Excel. Okay, how to make 3 cells the same? You can make one cell, you can make equal to a value. You can, I don't know if you have. Okay, you are probably now using Solver. Okay, Excel Solver. Okay, this solver here, okay, and if you see what solver can do, say one cell only. This cell I can either maximize, I can either minimize, or I can have a value. But I don't know what value that number might be, okay? So that causes some issues because I cannot make 3 cells to be the same. Let's make that small comment here. Okay, only one cell, only either to maximize, minimize, or make equal to one cell. Okay, I can do only those operations. So one way I suggest you try. Okay, you can do all kind of ideas. Okay, there are all kind of ways to solve this problem, but one way I say, or that I suggest, is you compute here the P average. Okay, you can use any approach, but you say here is the P average of the junction. Initially, probably the values are going to be very different because you assume a PWF which is far away. Okay, now you define here an error. Okay, that will be, you have different ways to define it, but you can define Pj minus the P average squared. Okay, Pj minus P average squared, Pj And you're going to see now why. So we have first the difference between the average and the actual value. Okay? When I have a solution, those two numbers should be the same. Okay? All of these three are the same, therefore the average is unique. Okay? If I have this, if it's different than 0, it means that the PJs are different. Okay? And now what I do is that I sum all of them up. And that's why I have the square. Okay? Might be that some value is greater than P average. Might be that some value is lower than P average. So one is negative, one is positive. When I sum them, it gives me 0. Okay? But that's not correct. They are not the same. So that's why I make it square. Okay? Or use absolute value. And now this I can use as a solver. How do we maybe move this to the side? Okay. I use this guy as my objective function. Okay, as the objective function I have here. Okay. I want that cell to minimize it or to make it to 0 by changing which cells? The PWF1 that I assume and PWF2. Okay. And then you click run and you find probably it's not so easy. You have some problems. You will have some issues, but in principle that's that. Okay, let's take before we take a break. No, we take a break first. Okay, let's say 15 minutes. Just one comment about there are some people concerned about the exercise set 2, the values they are getting. Okay, some of you are saying it's negative, it's a negative project. So why this guy Equinor went for it? Well, it's very much in the margin. Okay, it's not such a that always is very robust, always going to be positive. Okay, so don't be as scared if you some cases you find negative numbers. Okay, for more questions we have to ask someone that was involved in the project, but year after year the people participating in this course have found that it's actually very close to negative. It's not so. It's not very robust. But also there comes the other aspect of field development. It's a very strategic position, right? For any future fields in the Barents Sea, if they have a gas facility, then they can transfer the gas to that place and then ship it. Okay, there is nothing else there. You don't have any pipeline. You cannot connect this gas to any place. So this gas, the gas production becomes actually a problem. You have to re-inject all of this gas. Okay, and that costs a lot of money, resources, and you're losing money. So if they have a base, Equinor, that they have an LNG plant, after Snow White is finished producing, they can say, well, now we are offering, who wants to send the gas here? Okay? So I think I'm speculating, but I think that's part of the reason why they also went for the project. Okay, so now we have discussed roughly networks. How do we solve it? The different ways, how do we solve it? Some things to help you to understand a bit better networks. And how, for the exercise you're going to get, how you have to, a suggestion, okay, how you have to solve it. Remember, if you have a choke and the rate is feasible, you don't have to do any of that. Okay, you just have to calculate upstream, downstream, and verify, just like what we have done for Snow White. Okay, now on the other hand, if you don't have enough energy, then you have to make this run to calculate rate. Okay, another complexity might be that you might get in the exercise. Okay, is having wells in the same network that are producing from different reservoirs. Okay, and that's typically in subsea systems. You have two wells that, or a few wells that are draining from a reservoir. Okay, and then you have the pipeline is going to the FPSO. Okay, but then you have another cluster of wells, another group of wells that are producing from another reservoir. Okay. And then you have to be careful when you calculate production profile in time. You have to take into account the decline on both, and you have to know how much you are producing in both. Okay, so your Excel sheet, instead of having only one PR, will have PR1, set1, it will have a GP1, okay, all conditions for one, and then you have PR2, set2, GP2, and so forth with time. Okay, so just be aware of that when you add more wells into the same network to calculate the production profile at a given time. You know how to do it, but then if you progress in time, you have to keep track of these guys, okay, for each reservoir unit you have. Okay, now I just want to I like to make a short detour on what else can we use network for. And it can be important when predicting the profile. Okay, so network solving, what we have done so far is called network solving, can also be used for downhole networks. And we're going to see now very soon what is downhole network. Okay. And that whole network, essentially, we can have, if we think about a multilateral well, where we have one main wellbore, that's where I make the drilling, but then it splits in different branches, okay, in different laterals. Each one of them is a lateral. So essentially, you have on the same conduit, all of them reach on the same junction, okay, on the same departure point. So that's a lateral. And in that case, to see how much is producing from each lateral, you have to use some sort, if they are very different, you have to use some sort of a network approach. You can also have, if you have multi-layer wells. Okay. For example, we have one layer up here, and we have one layer up here. And we are producing, we simply put a pipe inside, and that will be layer 1, and that will be layer 2. And it's extremely important not only to remember, we have to account how the layers, how the reservoir, they are essentially two different reservoirs. They are depleting differently. Okay? So it's very important to track how much is produced from one layer compared to the other. Okay? It's very important. And sometimes nature is not fair. So sometimes we can have a very big layer, okay, very big volume, but with low productivity. So that we have to produce slowly. And then we have a very small layer, but it's very productive. Okay? So what happens after time, one depletes quicker than the other. Okay? This pressure goes down quicker than the big layer. Okay? And therefore, part of the production, what might happen, okay? So if the layers are very different or deplete very differently, okay, then you might end up with the case that if we make a point, I'm going to make networks is useful that you transform, you try to visualize your system and you make it into a line equivalent. I think that's very useful for analysis. Okay, for example, in this case, you make a line equivalent where you have something like that. Okay, and you go here from reservoir pressure all the way to the junction, reservoir pressure to the junction. Okay, and here you have the wellhead. And here you can also do the same. You can say I have 1, then I have layer 1, I have 2, and then I have layer 2. That will be PR1, PR2. That will be this tubing section, and this will be this tubing section. Okay, and here maybe we have P wellhead. Okay, so essentially what might happen with time is that initially, okay, you have Q1, Q2, everything is happy. Here you have Q2, and here you have simply Q1 plus Q2. You are producing from both layers. But due to the depletion that you have, with time, it might happen actually that you have the following. You have rate going here, but then you have rate going into one of the layers. Okay, so you have one layer which is stealing production because that was already depleted. This pressure is much higher than that pressure, and then it's partly stealing part of the production. Okay, Q2, Q1. Okay, if they Q2 minus Q1. So far in our system, we didn't assume that there was any change of direction. Okay, in this system here, we don't say it's possible that you can flow to the other well. Okay, but you have to be careful. What do we put to avoid backflow on wells typically? To avoid that, you know, you're producing from this one, but this one is stealing production. What do you use if you're a plumber? You have to make that in your place. You use a check valve, right? One direction valve, or they call it also a Tilbake Schlagsventil. Yes? Okay, which simply is, so let's put here, let's make a small, now I'm taking a detour, but I think it's interesting. In wells, okay, a check valve is typically placed at the Christmas tree to avoid backflow. Okay, and a check valve, if we say we think in a very simple design, okay, can be simply a ball, something like that. Okay, let's make it, maybe delete that part. Okay, something like in a very simple, very simplistic way, it can be so simple as that. Okay, such that if you have flow on this direction, it allows flow, but then if you have flow on the other direction, it presses the ball against the seat and no flow. Okay. But however, in these cases, we don't have that in place, so you might really well have the option that that one is stealing part of the production. Okay, what we do sometimes to avoid this issue, okay, in wells, sometimes we use sliding sleeves. That means that in the same, let's make again the same drawing. So I make here some perforations to access the formation. Okay, but then I send in the pipe, what I do is that I isolate. I put some sort of a packer, I put some sort of a seal to isolate that formation. And actually this one I don't have to put a packer. Okay? If I don't have anything else below, I can do it like that. And then I put some component here. Okay, so it has to go from this annular space, the fluid, inside the tubing. Okay, so I have to make a hole. Okay, to be able to control the hole, I put something called an sliding sleeve. Okay, here I put something, and here I put something. Well, actually here I have to do it. Let's make the packer also here, just to make it simple. Okay, and this might be a sliding sleeve. We're going to see very soon what it is. We can use an eye inflow control device. Okay, or we can use a we don't need this, right? Or an inflow control valve. Okay, like a choke, inflow control valve. This is essentially a choke. This I make the abbreviation ICD, and this is ICV. Okay, but basically in a choke you get the idea. You try to choke. If you're getting some rays from here, you try to close or even to choke, okay, the formation. Or if you want both of them to be depleted evenly, if you're getting too much flow from one of them, okay, like from Q2 for example, or Q1, you try to choke that formation such that both deplete at the same rate, okay, at the same. And I think I have like a small animation or a diagram of that. And that's how, for example, a sliding sleeve looks like. You have that on the compendium. So you have basically two pipes that are one inside of the other, and the red pipe is free to move up or down. Okay, if you see here, it's not so simple, but here you see it has some sort of a locking mechanism. Okay, so I can push it down, and it will come outside of this. You see here in the wall there are some how do you say, some grooves. Okay, there are some holes, but if you push it down, it will now lock in the next groove here, the red part. Okay, so you can move it up and down 3 positions. I have a groove here, I have a groove here, and I have a groove here. Okay, so depending which one it is, here are the holes. Okay, the holes that connect the outer part with the inner part. Okay, so depending how are the holes aligned, here I have a big hole. Okay, if that one is aligned with this one, I will have flow inside the tubing. Okay, if it's not allowed, if it's not aligned, if I just have a blank pipe, I don't have any flow. Okay, so simply by moving this one up and down, I can regulate if this is connected or if it's not connected, closed, or I have here I have just connected and not connected. Okay, so just a small a short comment on that. Okay, you can have also networks very complicated. You can have these ICVs, ICDs, a sliding sleeve, and then I have to make almost like a subsea network. Okay, you have to make an analysis like that. Then I have one more case that I wanted to say. So we have multilateral, multi-layer. I can have also a horizontal well can be treated like a network. Horizontal well. Okay, so let's look at the well, for example, where we have a horizontal well. Let's make it open hole. So something have been drilled here. That's my well. Okay, and then I have, that's the layer of oil. Okay, and here let's say I have water. Okay, I have an aquifer which is supporting production, and then at the top I might have also gas. We can put the gas if you want. Okay, and of course the scale is very exaggerated. We don't have such big holes in the formation. This is something typically like maybe 10 meters, 20 meters, and this should be something like 9 inch. Okay, so it's not to scale. So if you plot, now I'm going to plot the pressure. Let me just move it to another page. Okay, I want to plot now, let's make a plot here of pressure versus length versus x, a parameter that I call x, okay, the position, the axial position. So what happens if you plot PWF, or the pressure inside the tubing, okay, inside of this hole? What happens if you plot that pressure along the distance? We're saying it's a horizontal pipe, right? To have flow from one place to another, simply the pressure should be higher, right? And the flow here is going on this direction. Okay? Therefore, if you plot the pressure inside the hole, it should be something like this. Right? This will be my like PWF pressure, the pressure inside the wellbore. Yeah? Now you remember that for the case that we discussed before, the Q of oil, for example, of an undersaturated, you remember the equation, right? The equation was JPR minus PWF. But in this case I have a variation of PWF. Okay, the rate that I have will be given by the difference between the reservoir pressure, which is constant for all of them. Okay, let's put here PR, by that difference. Okay, so when I have a high difference, what should happen? I have a higher rate, right? Okay, so if you plot the rate profile of this well, let's make another axis here. I hope it doesn't get too messy. Q oil. How should the rate profile look like? It should actually be something like this. Okay, increasing, 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 increasing. Okay, therefore you're not draining in a uniform way that oil layer. Okay, you're draining more from the part close. That's what we call the heel of the well, and that's what we call the toe of the well. So we are draining more from the heel and less from the toe. And because of that, what might happen is that you might have at the end eventually coning. Okay, you have breakthrough, either the water to the heel or the gas to that heel. Okay, so one way I can analyze this problem is to split it. Okay, I can split it into, or to study this problem, I can split it into a network actually. I decide the number of points. Okay, and then I have here a reservoir pressure, which will be in this case the same for all of them. Okay, so here I have reservoir pressure. That's my IPR equation in each one of these boxes, and then I should add one more box where I have my pipe. Okay, pipe PR. Okay, my pipe PR equation. Okay, so I have again to say how much I'm draining from each section. Then I have to sum up In this section I will have only this rate, this section I will have the sum of both, and so forth. So if you see, there are many equations I have to solve. Okay, I have to solve 1, 2, 3, 4, 5, 6 equations, 7, 8, 9, 10, 11, 12. And then on top of that, I have mass balance in every node on that. Okay, so it's a huge set of equations I have to solve. That also I do using network. Yeah. One thing I make. Yeah. One thing I make to improve the situation. Okay, to improve drainage. I sometimes use, so I have, again, let's make my hole once more, okay. And then I put a pipe inside, and then this pipe will separate with this sort of seal or packer. It will separate by region. And then for each one of these regions, I can put exactly the same thing, the sliding sleeve, the ICV, AICV that we discussed before, right? To try to control. If I have too much pressure drop, I can just too high delta P, okay? I can simply add some artificial delta P, okay, to try to equalize production. Let me just finish the drawing here. So I try to separate in compartments the flow from the reservoir. And then I try to say how much I'm producing from each compartment. Okay, and then I make, so the equivalent system will be, I have PR, I have then IPR, and then I put here another pressure drop, which is the ICD or ICV or a sliding sleeve, and finally I reach this PWF. Okay, and then I have pipe PPR. Okay, and then I go another pipe PPR. Now in this case inside the tubing, okay, inside the liner. Then I have once more another ICD, IPR, and PR. I'm going to make 3, okay, only. Okay, and essentially, if you're getting different rates through each one of them, Q1, Q2, and Q3, okay, I have to change the delta P across the ICD such that I get the same rate. I get an even distribution of rate. So the idea is to change delta P across each ICD to get that Q1 is similar to Q2, is similar to Q3. Okay? But for that I have to make this change. Okay, this was a very simple case. I don't need any components, nothing, can be open hole, but I can have just one hole. Here I have to make these packers, I have to separate, I have to put a liner inside, and then I have to put this control element. Okay, this element that I can change. Okay, and then I have to regulate to get that. More or less clear? Yeah. Okay. So with that, I think that's all I wanted to say on networks. Okay, for production profile, for our field development analysis, it's important to know, because this well is significantly more costly than this. This well is significantly more costly than this well. Okay, so it's very important, if we are going to need something like that, to understand why do we need it, and really to justify that can be a very high increase in the cost of a well, okay, just to include so much equipment. Especially if I want to make it that I can adjust it, okay, from the surface. I have to pull a line, okay, I have to put a hydraulic line through here to enter into this one, and then I have to put one going to this guy, and then I have to put one going to this guy, depending how many I have, to be able to regulate this choke, okay. I want more choking, less choking, and how that's going to change, okay. For example, if I know that one of them I'm going to get water breakthrough in the life, or I get water breakthrough, then I have to close it, okay. And that, if I want to have that option, that's going to add cost. But really the other important effect is if I have this multi-layered system, multi-reservoir producing from the same well. Be careful, I have to keep track how much is produced here, and if I stop for any reason production, I don't close, I have both of them are communicating, one is going to charge the other, okay, one is going to gradually charge the other layer. So that becomes complicated when predicting production profile, all kind of things. Okay, now let's go to the last part of this lecture, and we are going to talk about boosting, okay. That's the main topic. We're going to be working this a bit and part of next week. Boosting. And boosting means simply adding energy to the fluid. It's typically a pressure increase. Okay, and I do that such that if I make a simple drawing, okay, of a well, I have here an element which is going to add energy. Okay, and then I plot, let's say, pressure at the wellhead, pressure at the junction. So I plot both. Okay, and that means if I want to produce on a rate that is on this side, okay, I have less energy than what I need. And that can happen, let's say, when I'm reaching the end of the plateau, I simply want to prolong it. That's what's going to happen in Snow White. They're going to put a subsea compressor or a topside compressor just to try to make that match, okay. But it can also happen from the beginning of the life of the field, okay. Maybe the field, if I don't put anything, the rate that I have is non-economical. This rate has a very low, okay, low payback. So that's why I need maybe to include something to bridge that, to increase rates such that you take it to the economic level, okay. And that's typically, for example, for viscous or low API fields. Low API, high viscosity. Okay, when you have a high viscosity, that creates a lot of pressure drop through the pipe, and then you need sometimes to get reasonable, profitable rates. You need to have this bridging. Okay, so you can have the design from the beginning, very important to see if you need it or not, or you can have it later in life just to maintain production. Okay, so there are two ways from the beginning. Okay, to get profitable production. Or you can also do it, later while production. And this is simply basically to maximize plateau. Okay, to prolong plateau, not to maximize, but to prolong plateau. And there are different methods. Okay, we can make this also, they can be applied two different types. I can apply it on a well level, and this is something that we call artificial lift. Okay. Or we can apply it on a system level. And here typically is where we have this boosting. Okay. In well level, we serve one well separately. This component will be simply for one well, and in a system level, we do it for a group of wells. Okay. So, yeah, I'm going to talk about boosting. Typically, this type of boosting is typically two-phase. Okay, that means that I have a multi-phase mixture inside. I have gas and oil. Some gas already came out of solution, or I had gas coming out from the formation. So I have gas and liquid flowing through the pump. Okay. Or I can typically have gas, okay, gas compression. Okay. Or I separate, which is not that common, separate and pump gas and liquid separately. Okay, so I can do everything in one go, two-phase. It's a machine that can take everything. I can do simply, if I have a dry gas or some gas which doesn't have much liquid, I can do simply gas compression, or I can just separate both streams separately, pump through a pump and compressor, and then merge. Okay, so but I think to understand, just to jump directly on compression, remember what we are looking at a higher level, right? Is basically from here we're going to get a combination of Q star and DP star, right? And then we want to see if that combination is feasible. Okay, we want to see the main point, or our main objective for production profile, for field planning, is this combination feasible? We know with choke we don't have to worry much. It's very wide. You can change the opening, you can change the size, you can change many things. Okay, for pump and compressor is not so easy. Okay, the envelope looks very different. If you're going to plot the Q versus delta P that you have, okay, the collection of points that you need, the area, operational area, let's make it like that, operational area of pump or compressor, okay, it should fall inside that area. If the points fall outside, then you cannot produce these rates that you are planning. Okay, so that's what we are looking for, how that area looks like. But to see how that area looks like, we have to go a bit deeper, not too much, but we have to go a bit deeper in how the compressor and the pump work. Okay, how many of you had some class about pumping or compression before? One? Okay. Okay, it's not a big problem, but we have to understand, go a bit in detail how the machine works to find out this area. Okay, and then we do exercise. And to start our explanation, we are going to start with artificial lift, because it's a bit simpler, and we are going to start with electric submersible pump, okay, or abbreviated ESP, and that's a pump for mainly liquid. Okay, so we go liquid is always slightly simpler than gas, and then we go and maybe next week we go and migrate to how for compression, gas compression, how it looks like. Keep in mind for subsea, you always, almost for all cases, you have gas. You have to compress gas or a mixture of gas and liquid. So it's very important to see how the compression of gas and liquid works, okay, to understand. But before that, I think it's good to go just to pure liquid. Okay, that's what we are going to do now. But before we start then, let's take another break, okay? Let's say early break, 15 minutes. We come back here, it will be 12:10, okay? For the last part. In the last part of this class, okay, so the electric submersible pump is typically installed as close as possible to the formation. Okay, if we have our wellbore, we have our perforation someplace here. We have our formation someplace here. So you try to install it. Actually, it's part of the tubing string. Okay, it's screwed on the tubing string. Okay, so here you have this ESP module. Okay, and that basically gives the boost. So when you make your equilibrium calculations, you make it at the bottom hole, typically. PWF, so you get one curve, which will be simply the formation or the IPR, and maybe some height difference, not much. And then you have your tubing, we call this equation TPR, the tubing, and that will be the pressure at the discharge. Okay, on the pump we typically can define 2 points. One of them is the suction, and in our case the inlet to this pump is on the side. Okay, we are going to see now how it looks like, but the inlet is on the side and the discharge is inside of the tubing. So this is P discharge and this is P suction, which is very similar to PWF. And this pump is running actually with electricity. Okay, so we have to make a hole here to pass a cable to connect the pump to power. Okay, to connect it to the grid. The way the way it goes, very roughly, I don't want to go too many details, okay? But the way it is that you have, typically you have a motor. Let me make it maybe bigger. Okay, and the motor, the idea is that that motor gets hot, okay, because you are rotating all of that, pump. So the idea is that you put it in a way that this fluid can cool down the motor. Okay, remember this might be quite hot, okay, 100 degrees, 80 degrees, so that means that the pump motor is much hotter than that. Okay, then you have another section where you have, and this, if the P suction is less than P bubble point, okay, there will be gas. Okay, if we have the phase envelope of the reservoir, PET, it's something like that, and we are at reservoir temperature, you should be, that's a part of liquid, and that's a part of liquid plus vapor. Okay, so you should be inside of there to have only liquid going through the pump. If not, then you have to have this gas liquid separator. That means that the fluid here, you have a mixture, can be a mixture of oil and gas coming inside. Okay, then you separate. You have another module here that's actually where the pump is. That's the pump. Okay. And the gas, the liquid continues inside through the pump, but the gas flows outside through the annulus. Okay, but remember, if I have this gas flowing through the annulus, I have to have a way where to take it. So I have to take out in the well. Okay, if I continue up, this is not up to scale, but if I continue all the way up, I have to have a way to drain that gas, okay, to produce that gas. So I have to make here a hole. I have to put a pipe and a valve, so just to be able to produce the gas. And that's not really typical in offshore field. Okay, you don't produce gas through the annulus. And it has to do something with safety. We have here typically something that is a safety valve. If something happens, that's going to close, okay, and close all production from the well. But when we have flow through the annulus, actually we have a leak path. Okay, if something happens, the reservoir is completely connected to that annulus, okay, without any safety. So if you want to use that approach, you have to add a safety valve, which looks very strange. It's like a seal with an opening, okay, or through which the gas can pass, but if something happens, it has to close. So it's very complicated, difficult solution, but and that's why it's not too much use. It's used a bit, but not too much offshore. Okay, because of that, but just that, you know. Okay, so that's how it looks like. The motor at the bottom, gas liquid separator if you need, and then the pump at the top, and then the fluid simply flows through the pump and goes through here. Let me show you some yeah, I think it's nice if we take that image. Okay, so that's how at the wellhead you have here. I think that figure is nice. Okay, you see here, that's the tubing. The tubing is hanged, all the weight of the tubing is hanged on this is at the surface. Okay, people can either with ROV, or if you have it on the platform, people can have access to this part. And then you have this opening through which the cable goes through. Okay, so this guy here is the tubing hanger. We're now go a bit into completion, not much. Tubing hanger. Okay, that's the power cable, which can be very thick, and that's the tubing here. And that goes maybe 1,000, 2,000 meters down, all the way where the pump is. Remember, the pump is screwed onto this pipe. Here you screwed, and then you have the pump screwed to that pipe. Yeah, the power. So yeah, that's another thing interesting. The power system. So I simply take the power from the grid, take the power from the gas turbine. I have a transformer to get the voltage of the pump. Okay, and then I have I control basically the rotational speed of the pump. I control it with the voltage. Okay, so if I have more voltage, does it go faster or slower? We don't have any electrical. I changed not the voltage but the frequency. Okay. No electrical engineer here. Yeah. High frequency, more speed. Less frequency, less speed. So you've changed the frequency of the power such that you can change the rotational speed of the pump. Okay. And that's a way you have in land. That's a bit not for offshore. You have the transformer. You have this variable speed drive to change, and here you have the cable. Okay, this box is yeah, it's for land. Offshore also, don't worry about it. So let's see, the pump Oh yeah, I'll show you how it looks like. So the pump part looks like that's one stage, okay? It's made of multiple of these ones, one on top of the other, on top of the other, okay? Such that the fluid is, and it's actually this way, okay? So the fluid is entering through this small annular section here. This is rotating, okay? Then pushes the fluid out, okay? And then the fluid is coming in back here again, okay? Going through it, and then is directed through this annulus through the next stage. Right here. Okay? So you have a bunch of them which are is like a pancake of a lot of them, maybe 50, 100 of them. Okay? Fluid goes through the annular section, this is rotating, okay? Fluid comes out, goes inside here, is redirected again to the center, and then comes out through this part. Okay? And you see very carefully, there are two details very interesting here. You see, I don't know if you see it here, but there is a groove. You see on the internal face, there is like a slot. I don't know if you see it. So it has an axis that goes connected to the motor. Okay, the axis goes all the way connected to the motor. And that axis actually has a small groove also itself. So let me maybe show you with a Okay, so you have the axis, which looks like that. Okay, and you have this rotor, which looks like that. Okay, but then to connect them, because one is rotating, this one also has to connect. You need to have a mechanism which is called a key. Okay, so you make a groove here, you make a groove here, and you put a piece of metal in between. Okay, to hold it. Okay, that's what we call a key. I think I have a better okay, a key, something like that. Okay, and also note something else. So that means it's not really holding the weight of the impeller. Okay, this is simply passing through, and when it rotates, it makes it rotate. Okay, but the weight is not being held by the axis. It's actually able to move on this direction, on the vertical direction. Okay, that means that the weight is going to be held by, if you see here it has like an annular space, okay, and you see here it has also the same annular space made, okay, such that it's held by that. And that causes some very interesting, you see, why are you talking about this stuff? Okay, this causes something very important in the DPQ chart of the pump. Very important, very, very important. Because when this one is way too much on this part, okay, it's making too much weight, it's actually, there is a lot of wear and erosion on this part, okay? When it's pushing too much on the back, it's also causing too much wear here on this side, okay, when it's pushing like that, okay, because it's able to move like that, and the way it moves, it depends on the flow, how much flow is passing through it. If there is a lot of flow, it will be tendency to push up and have a lot of drag here. If you have too low flow, then it tends to push too much down, and then you have a lot of erosion on this area here. Okay? So now I'm going to pass it so you can take a closer look, but we are going to see. So you might think, why do I care? You know, you show me the metal I don't like, you know, I just going to do simulation, I don't care. It has some very fundamental consequences on the modeling part. So where was this? Oh, just for some historical reason, here we have the name of the inventor and the way the rotor looks like. Okay, so here this should be actually upside down. Okay, that's down, this part here, down, and this is up. And the fluid actually enters through here and then escapes through that place. Okay, that change in momentum that you have here is going very slow and here is going very fast. That's what causes the increase in pressure drop, the increase in pressure. Well, you add energy and then you and let me put the name of this guy who looks very serious, but that's actually the inventor. A Russian immigrant came to the US, make a lot of money making pumps. Okay, but he looks like he's no joke. He can call the mafia on you, so be careful. Okay, so the behavior of that pump, if you plot the rate versus delta P, that's what we are looking for, okay, how it behaves. The rate versus delta P actually looks very much like IPR, okay, looks very much like an available pressure curve. But be careful one thing first. This Q is a Q. Remember, so far we are using the Q, the units is standard conditions per day. Okay, that means the rate that I will get at the platform, at the separator. This is not that rate. Okay, I'm going to put here a cross. That's not that rate. That's the rate at exactly at the inlet, at inlet conditions. Okay, so that's at inlet conditions. Okay, for example, if you look at oil, right? We are looking at, now I'm going to get a small detour again. Okay, here I'm getting some Q oil, okay, some rate of oil. But if I go any place in the system, I'm going to have the same Q oil. It's like a mass flow, okay? But you're going to get different QO, the at local conditions. Okay, why? Because maybe the oil here is simply pure oil. Okay, it's simply no gas coming out of solution. So this QO will be actually bigger than QO at standard condition. Let's say that this is 10,000 barrels. Okay, this one might be 12,000. Now, when you go on another place here, maybe some of the gas came out of solution. Okay, and you have oil. So in this case, the Q oil maybe is still going to be bigger than QO. Okay, but might be, I don't know. Here we said how much? 12,000, and here it might be 11,000. Okay, because of this gas that you're losing on that. So be careful. This plot is local. This is local conditions, and that tells you that the pump, the power of the pump, okay, the power of the pump is basically the energy, right, that is delivering, and that's delta P times Q divided by the hydraulic efficiency. So if you see this chart, it means if I have, the pump has a motor, right? It has a fixed motor. It has this motor that we install here down, and this might be 100 HP horsepower, 120, can be 600 HP, something around that, right? So if I have that energy, which is fixed, okay, I can do two things, right? I can have a very high rate, but then I will get a very low delta P, okay, which then I'm going to be here. Or I can have a very low rate, but then I can have a very high delta P with the same energy. Okay, so that's part of the reasoning why the curve looks like that. When I want to increase the rate, then the pump can give me only a few bar. When I want to reduce the rate, then the pump can give me more. Okay, and remember, this is for a collection. This curve is for a collection of stages. Okay, that means I have one after the other after the other. I have many of them in series. Okay, pumps in series. Okay. Now that equation, it's typically you use for that equation. Typically we use the pump equation. Okay, we have delta P of the pump is equal to the density of the mixture. You might have water, okay? And actually in the exercise we're going to have water. And then that times an equation that looks something like that. A Q B Q okay, with some coefficients that okay, if I have a number of points of testing, this pump I tested in the lab, I get a few points, then I can find out exactly, with a trend line, I can find exactly A, B, C, D, and E. And if it don't match very nice, then I can increase the order of the polynomial. Okay, I can use more or less. But typically number 4, number 5, even number 5 sometimes are used. Okay, now what happens when that's for a given rotational speed, okay? That's for a given frequency 1. What happens when I increase the frequency? I make it rotate faster, this pump. That's something I can adjust, right? I just come here to this box, yeah, and I change the frequency. How does the curve change? What do you think if I rotate faster? I should give more energy, right? Because remember here, energy is, what is yeah, we don't go to that. Okay, but basically, if I increase the frequency, I should have something like that. Frequency, let's put this one 1, let's call this one 2. Okay, if I reduce the frequency, I should have something like that, F3 and F4. So basically, increasing the frequency gives me higher delivery, pump delivery. F1 greater than F2, F3, F4. And the frequency for these pumps typically goes between, someplace between 30 Hertz and maybe 70 Hertz. That's the range of frequency. So that tells you, in theory, right, if we are looking at if the point is feasible or not, it will say, well, everything that falls inside here, if my point, my combination of dp, now I spoiled the plot, right? But everything that comes, if I have a q and dp falling inside here, I should be able to produce that. Okay? Not so simple. So let's go to the next complexity. Okay, this delta P for another frequency. Okay, I do is again rho of the mixture of, and then I change A times Q F reference divided by F. Let's do the 4. Okay, that's how the equation changed. You don't have to go too much in detail here, but that's how I calculate the equation for a different frequency. Okay, and that's because it's some kind of dimensionless property. Okay, if I have, for example, I make the curve, I calculate the coefficients at coefficients calculated at F reference. Okay, and the reference frequency is typically 60 Hertz or can be also 50 Hertz. Depends on the place, but that's the place where they make the runs, the testing of the pump. Okay, but then if you want to calculate for another frequency, I simply have to multiply the Q times F reference divided by the actual F that I have. Okay. Okay, and but that equation has been programmed for you in the exercise you're going to get. So don't worry, but just to show you slightly where it came from. I'm going to take the okay, let's put here, there is another constraint to the pump map. Okay, and that's what we call the up thrust and down thrust region. And that's when we have this kind of pump, which is floating impeller. The impeller is not fixed to the axis, it's simply floating. And I think we can use the image from the compendium. Okay, here okay, so for the same reason that I mentioned before, okay, so that's the same, right? The same curve of the pump for different frequencies. Okay, and I have here's something I didn't mention, this hydraulic efficiency you had in the power. Okay, the power is delta Q delta P times Q divided by eta H. Okay, this one has a maximum point, a point where it is maximum. If you plot the efficiency with the rate, okay, it should give you something like this. It has a peak. Okay, that's the point, the rate at which you have the maximum efficiency. So if you plot that point for all frequencies, you see that that's the best rate to operate. This is the best rate that gives you biggest highest efficiency. If this is very big, that means that the power you need, okay, that the why it doesn't come up. Refusing. Okay, if this one is big, that means that the power you need is small. Okay, that means instead of having to buy a motor for 600 horsepower, 200, you can buy something smaller. Okay, now here is related, these two lines are related to what happens with this floating impeller. Okay, if you float too much to the right, then that impeller will be pushing to the back. Okay, because the flow is just too high, and then you will have a lot of erosion on the back of the impeller, what you have there in your hands. If the rate now is too low, that means the impeller will be just laying too much weight while it rotates on the lower part. Okay, and then you will have too much erosion. So that's why we define these two lines, which is the line of up thrust and down thrust. That's up thrust and down thrust. So if you want your pump to have a happy life, long happy life, you should be between these two lines. That means that the area of the pump ends up being, remember we have all of these guys for different frequencies, F max, F min. Okay, and then we have these two other lines which look something like that. Okay, that means that the area, the feasible area of the pump is actually this one. That's the feasible operational area of the pump. Your points have to be within that range. And if they can be close to this best efficiency line, as close as possible, that's best. That's the pump designer. They try to select a pump where all of your points that you give them, the line passes through it, which is a very challenging task. Okay. Yeah, I just want to show you another reason why you want to be between a minimum and a maximum is because of efficiency. Okay, so I think that's a very nice figure. Okay, it's here. And here is all the reference to that presentation, but that was actually measurements. Okay, those are people managed to measure. So the way why it happens, why you have this decline in efficiency, here is the rate, right? You have your best efficiency point, and then you're reducing the rate. Okay? The blades, the passage from the center all the way to the end, they are made for a specific rate. If you have the best efficiency, you see the flow lines, they follow exactly the passage, no recirculation. When you start reducing the rate, the flow actually enters in a different direction. It doesn't enter anymore in this direction, but now it enters slightly like that. And you see, you start having problems here, some recirculation. Okay? And here it gets worse when you reduce more the rate, and here it even gets worse. And the problem is that you block part of the channel. Now the channel that you have for flow is actually much less. And this recirculation is what causes this, the drop in efficiency that you have on this side. If you go in the other direction, then the angle goes the other way, like that. Okay, now you have a pocket happening here, and you will have the same on the other direction. So that's another reason why we try to limit our operation within these two, extremes. Okay, now that you understood, let me just show you how, for pump manufacture, how it looks like. Okay, that's a pump for a field from Statoil, called Peregrino, from Equinor now, right? We cannot say Statoil anymore. Okay, and that's how the area, the envelope of the pump looks like. For different pumps, I think they have pump one stage is different models. Okay, they have different models. So now let's go back to, this head. That's something we didn't discuss. This head is actually the delta P of the pump divided by the density. Okay, that's what we call the head. Delta H, or is the head. But it's equivalent. Okay. Now let's go back to and with that we finish class. We have had a long session today. Okay, so we have ESP here, then we have our formation, and then we have, let's say we have very close the separator. Okay, we have that system, and we make our two curves, the available and the required. Okay, that will be PWF, and it will be P discharge, and that's the rate, and I now want to operate here. Okay, that's my delta P versus Q star. Okay, now let's plot that. Okay, that combination delta P star and Q star on the operational map of the pump. Okay, now we go to the operational map of the pump, delta P versus Q. That's Q at standard conditions, and this Q is local. And we know the curve looks something like that. And let's make initially the assumption that Q local is more or less similar to Q standard conditions. Okay, that means no gas is coming out of solution. Which is not true, okay, but it's just to make our life simple. So let's say we have Q star and delta P star, and it falls here. I try to find, of course, a pump, right, where this point falls very close to the best efficiency line and maybe in the center. What happens now with time? How is this plot changing with time? the intersection. What did we say? Time affects which curve? Does it affect this curve? The tubing and the separator? No, right? The pressure at the separator will always be the same. So depletion, what will affect is reservoir pressure. That means this curve here. Okay, so as we discussed before, reservoir pressure affects in a way that it makes this to go down, right? So the Q star will be always the same, right? But what happens with delta P? With time, it starts to be higher and higher. Okay, so you have with time, PR is reduced. Okay, and that means that delta P star is increasing. So if you make a plot of that, the Q, if we make the same assumption, but the delta P then will be higher, higher, until, remember, I cannot go outside of this region. To go outside, I have to use a frequency which I cannot physically achieve, right? A very high frequency. So that means I have to reduce the rate. Okay, I cannot deliver that rate anymore. Okay, and then I try to produce at maximum, so to get the most out of it, but then I move on this direction, trying to reduce the rate to go on that direction. And that's the exercise you're going to make. Okay, you have to calculate this Q delta P versus time, and then see if you are inside the region. If you're not inside the region, you have to correct the rate. Okay, but basically that's how the process looks like, going up and up and up, and then going to the left. Of course, when you start to deviate, you start to get outside, far away from the best efficiency line. Okay, and that's a challenge. Here your pump will be less and less and less efficient. Okay, I think that's all what I had planned to say today. We have to still to cover a few more details so you can make the exercise. How are you going to make the pressure drop calculations? This is liquid, so we have to go a bit away from gas and cover liquid. Oh yeah, just one thing before we finish. Just I remember one thing. Viscosity affects the curve of the pump. Okay, and that means if you have your Q, your delta P, you have for a viscosity 1, for a viscosity 2 it will be reduced. It is an effect similar to the frequency. Okay, when you reduce the viscosity, when you increase the viscosity, you get less delta P from the pump. And that's because the fluid has to go through all of these passages in the blade and in many places, and you have friction losses simply. Okay, so that's why when you have viscosity, you have also to change the shape. So on the exercise you're going to make, you're going to look at this detail. Okay, how is this dP changing, if the pump we have is suitable for the field, but you're also going to be looking a bit into that. Okay, and that we make this Peregrino field that was mentioned here. It has also water production, and the water production is increasing slowly with time. So when the fluid is more water-like, it has a viscosity similar to water. When the fluid is more oil-like, has a viscosity similar to oil. So you will have effectively a change in viscosity also during the life of the field. Okay, now we close. Any question before we close? No? Okay, see you next week.